Hi all, so we've got our video on nuclear fission and fusion, which is in the SL Energy course. So as always, we start with our study guide, and we are going to be covering all of these, all of them. Yes, yeah, pretty much. I mean, apart from the ones that they specifically say we don't. So, just starting with a quick recap of year 11 atomic theory. So, the nucleus is the block of matter that is inside the center of our atom. So, our nucleus consists of neutrons and protons. Yeah. E-U-S. So our nucleus contains those protons and neutrons. It makes up somewhere north of 99% of the mass of an atom. And in all of the chemistry we've been studying so far, we've been talking about how the electrons act. When we move it into nuclear energy, we're talking about how does the nucleus do stuff. So remember, when we're talking about the nucleus, we are only talking about that central block of the atom, and it is just those neutrons and protons. So binding energy is a key concept in nuclear physics. So it's basically the amount of energy that holds our nucleus together. So the analogy I've got here is for bond formation. So remember when we were looking at bond enthalpies, and the carbon double bond oxygen has a higher bond enthalpy than a carbon single bond oxygen. So the amount of energy that gets released when that carbon double bond oxygen forms is greater than the carbon single bond oxygen. In some ways, that's similar to nuclear bonding. As our nucleus becomes stronger, its binding energy increases. And you'll see on the next two slides, I've inserted graphs, but basically we've got our sort of peak, that most stable nucleus. Everything that's lighter fuses to get up to that peak. Everything on the other side fissions to get to that peak. So the stronger that nucleus, the higher the binding energy, the more likely it is to move towards that point. Okay. So over the past couple of years, I've talked about, sorry, this is energy of a nuclear reaction. Over the past few years, I've talked about conservation of mass, that we can't create or destroy matter, which is why when we write a chemical equation, it needs to be balanced because we can't be creating or destroying atoms. Nuclear reactions don't quite play by the same rules. They do in a lot of ways, which we'll discuss in a moment, but the energy of a nuclear reaction comes from the most famous equation in modern science. It's E equals mc squared. So let's break down what these letters mean. So E is energy, M is mass, and C stands for the Latin word celeritas, which translates as swiftness. You don't need to know the Greek or Latin, one of those. You don't need to know the etymology. I'm just giving that to you because I'm a nerd. So celeritas means swiftness, and it is the speed of light in a vacuum. So basically what happens when nuclear reactions happen, there is a tiny amount, laser pointer, a tiny amount of mass that is liberated. And then by multiplying that by the speed of light squared, it gets turned into energy. So if I lose even a fraction of a gram, because I'm multiplying it by this massive number here, I get a massive amount of energy out. So according to one paper I read, and it was some years ago, so that could have changed, in the Hiroshima nuclear attack, there was 0.1 gram of mass of the bomb that was converted into energy. Now, I'm not recommending you look at pictures of the survivors of the Hiroshima nuclear attack, mostly because they are quite harrowing. But even if you look at the US Army overhead, like aerial shots of Hiroshima before and after, you can see what 0.1 of a gram of matter can do. Let's continue on. So just a quick reminder before I get into these guys, when we are writing symbols for these particles that are in nuclear reactions, if you remember, when we're writing just general atomic symbols, we have the chemical symbol. Then up the top, we have the mass number. And down the bottom, we have the atomic. So for a proton, it has an atomic number of 1, because remember, atomic number is the number of protons, and it has a mass number of 1. For a neutron, it has a mass number of 1 and an atomic number of 0. An electron, which is an E- for reasons that will shortly become apparent, it has an atomic number of -1 and a mass number of 0. Electrons, I'll talk about that more later. Sorry, let me just finish the rest of these and then I'll come back and talk about the 3 main types of radiation. The helium nucleus is He2+. It has an atomic number of 2 and a mass number of 4. A positron is something the size of an electron, so a mass number of 0, but it has a +1 charge. So if you've ever heard of a PET scan, that is positron emission tomography, and it is a form of medical imaging. And then you've got gamma radiation, which is just a wave. So we tend to just give it the symbol gamma. So you've probably heard of the 3 main types of radiation. So we have alpha, beta, and gamma. So alpha radiation is our helium nucleus. Beta radiation is that electron. And then gamma radiation is just a wave. So I probably shouldn't say particles. I should probably put particles with inverted commas. Okay, let's continue on. Okay, so the most common place that we think about fusion reactions happening is in the sun. Fusion is an area that a lot of research is going into. However, we have real trouble working out how it might work in a place that is actually cool enough that we would be able to sustainably run it on Earth. So nuclear fusion is with those nuclei that I've just highlighted. Mostly where we think about it happening is in the sun. So a lot of the time, nuclear reactions that you'll be looking at involve isotopes of hydrogen and helium, because between them, hydrogen and helium make up, I can't remember the exact number, but I know that it's somewhere north of about 95% of all of the atoms in the universe. So let's look at an example of one or two of the different reactions that can take place in the sun. So if I start with a hydrogen, this is a hydrogen isotope called deuterium. And if I add to that another hydrogen isotope, that is tritium, that makes, so overall, my numbers up the top have to add up and my numbers down the bottom have to add up. So if the product of this is a 4,2 helium, what do I have left over at the top and the bottom? Let me just switch to a laser pointer. I need to place 2 positive charges, and I've placed 2 already. So this, what I've got left over is a 0. And then let's go back to my laser pointer. I need to place 5 mass, and I've placed 4, which means that this is going to be a 1. So something that has a mass of 1 and a charge of 0 is a neutron. So let's do this again. So if I put a deuterium and another deuterium together, and I tell you that we are making a tritium, let's go through the steps of how I work out what I need. So 2 plus 2 gives me 4, 1 plus 1 gives me 2. So looking at mass, I need to place 4 and I have placed 3, which means I need a mass of 1. I need to place 2 positive charges and I've placed 1, so I've got 1 left over. Something that has a mass of 1 and a charge of 1 is a proton. The other way that my 2, and that's a different green, but I can't be bothered fixing it. The other way that my 2 deuteriums can come together is actually to make a 3,2 helium. So let's look at what I need to place. 2 and 2 make 4, minus 3 leaves me with 1. 1 plus 1 is 2, minus 2 leaves me with 0. What do we call something with a mass of 1 but a charge of 0? A neutron. This is what we mean by constructing nuclear fusion reactions. Okay. Nuclear fission is our opposite process. So again, we split our binding curve at 56 and we say all of these guys undergo fission or splitting. Okay, so sorry about that. I just wanted to get an example of a nuclear fission reaction up on my phone because you don't actually have to remember any specific examples of these. You just have to, again, be able to construct them. So the one I'm going to look at for our purposes today is the one that is probably best known. It is the fission of uranium-235. Let me just go back to my pen. 235 uranium. So your first step is going to be finding the atomic number, which is 92. Then what happens? We add a neutron. That's part of the process. And we end up with this 23692 uranium. Now, when that's breaking down, it can break down in a variety of different ways. I'm only going to write out one of them. So one of the forms it can take is 1/3 139 barium, which is 56 here, and it can form 9436 krypton. Okay, there is another product here. I'd like you to pause this video and work out what it is we're missing. I just did a very silly thing and paused the recording, assuming that it was going to pause your recording of it. So how I would do this and how I did it on the previous slide, 139 plus 94, 139 plus 94 gives us 234. 56 plus 36 gives us 92. So how much mass do I need to replace? So 234, no, it's 94, not 95, it's 233. Sorry about that. So 236 minus 233 means that I need to place 3 mass and no charge. Now, we didn't have a subatomic particle that had 3 mass and no charge. However, what I could do is I could have 3 neutrons. And that's what ends up happening. This set of neutrons becomes important when later on we'll talk about nuclear power generators. Okay, so this is a quick recap of something we had a look at last year, looking at absorption and emission spectra. This diagram here on the right clearly shows an emission spectra. So you can tell that because the arrows are returning to the n equals 1, which means that they're releasing energy. However, for example, NASA can look at the spectrum that's being given off by a star and work out it's the proportion of hydrogen and helium that are in that star because of the rainbow of light that we see from that particular star. So we will see, instead of being a black box with coloured lines, which an emission spectra would be, what NASA sees from stars are what are called absorption spectra. So, excuse me a second. So, sorry about cutting myself off like that. I just wanted to quickly grab this picture here. So we've got that emission spectra, which is electrons falling down. And then an absorption spectra, which is electrons absorbing energy. Now, of course, this is the visible spectrum. These things also absorb in the UV, etc. The other thing to keep in mind is the Doppler effect. So the Doppler effect is, and we notice it with sound, if you're standing on a road and an ambulance or a cop car drives past you with their sirens on, you hear the wavelength of the sound decrease as the ambos drive past you. That's because the waves are getting stretched out. So what will tend to happen, this is the absorption spectrum for hydrogen, like in a close margin from where we are. But if these are coming from far away, there will be something called redshift, which is that Doppler effect. And, sorry, just finding a pen that I can write. These things will be shifted towards the red end of the spectrum. So that red shift is part of how we can measure the distance of stars from Earth. So these spectra are super useful to us, not only because they tell us about the composition of stars, but it can also tell us how far away those stars are. So there are two main types of uranium that exist, two main isotopes that are found naturally. There is 235, which I spoke about earlier, and then there's 238. So 235 is what is called fissionable. So it's able to be broken down comparatively simply. U-238 is stable. So we need to do something slightly different to it, which we'll see in the next slide, in order to get 238 to break down. So there was, until fairly recently, a deal between the United States government and Iran for the shutdown of its nuclear program. And one of the things that needed to be closed down was what was called enriching uranium. And as part of that, there are something called centrifuges. Now, centrifuges are basically a thing that spins super quickly, and it separates components on the basis of mass. So if I've got, as I would in nature, a mix of uranium-235 and 238, if I spin that super quickly, the more stable 238, the heavier 238, will move to the sides, and the 235 will stay closer to the center. I will put a video up on ManageBack with a physics person explaining it, because I'm sure there's more to it than that. But it is basically a centrifuge. There's then the idea of what's called critical mass. In order for a nuclear reaction to be self-sustaining, there has to be a certain quantity of uranium in order for that nuclear reaction to sustain itself. That's called the critical mass. And the critical mass for one fuel, depending on how reactive it is not going to be the same as the critical mass for another. So I showed you the reaction for 235 before, but let's just run through it again. So if I start with a neutron and I react it with 23592 uranium, I can end up making 14156 barium plus 9236 krypton, 3 neutrons and energy. So this is called a self-sustaining reaction. So it's sustainable because I make 3 neutrons, but only 1 is required to start this reaction. So I'm generating more neutrons than I use, which is why this reaction can sustain itself basically until I run out of uranium. So, but as I mentioned before, most of the uranium in existence isn't this 235, it's 238, which is far more stable. So in order to get uranium-238 to actually get energy out of it, I need to start by reacting it with a neutron, and it ends up forming 23992 uranium. Then, once I get there, I end up, that decomposes, so it gives off an electron, and it forms 23993 neptunium. Then it does that same decomposition again and forms 23994 plutonium. Now, the plutonium, so this is a breeder reaction, so 239.94 plutonium plus a neutron, that forms 14756 barium plus 9038 strontium plus 3 neutrons and energy. So when we say a breeder reaction, it is just that extra set of steps that we need to go through in order to get to the plutonium, which can then undergo fission. Okay. So half-life, by definition, and seriously, if you haven't played Half-Life the game, do it. It's awesome. So definition, this post is not sponsored. So definition, the definition of half-life is the amount of time for a radioisotope radioisotope's activity to reduce by half. So half-lives are a time. Now, there is massive variability in the half-lives. I just did carbon and nitrogen because they're next to each other on a periodic table, so it was really easy for me to look up this information. Carbon-12 is what's used in carbon dating. And that has a half-life of 5,700 seconds. So if I've got something that dies today and gets cut off from a carbon exchange, if I then, in 5,700 years, measure the concentration of carbon-14 in that organism, it will be half of what it would be on the day it died. Nitrogen-16, on the other hand, has a half-life every 7.13 seconds. It decays much more rapidly. Okay. So there's two main ways that we can work out half-lives. So 225 radon shows 1/16 of its original activity after 59.2 days. Find the half-life. Now, the first way we can do this is just by inspection. So if you can make the logical leap that 16 is 2 to the 4, what you then do is you go 59.2 div 4. So this number here is that number there. Hang on. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. Yeah, it's 2 to the 4. So 59.4. 59.2 divided by 4. Let me just get my calculator up. 59.2 div 4. Oh, no, I accidentally. 59.2 divided by 4 gives us 14.8. And it's really important that you remember to put units on. So the unit we've got here is days. So the unit that comes out at the end has to be days. Because the time frames we're looking at, this could be 59.2 years. You have to make sure you're writing down your time unit here. So most of the questions that you will see on this topic do fit this pattern. If you're able to work out 2 to the whatever, so 16 is 2 to the 4, 8 is 2 to the 3, etc. This sum is generally pretty simple. However, if you get stuck, there is another way to do it. So the other way you can do this calculation comes from the two formulae. Now these are straight out of the data book in that first section. So if we have n equals n naught, so this is the number of atoms, or the amount of activity, equals the amount of initial activity divided by 16. So this is the information we get from the question. Then we've got 1/16 is equal to a neg 59.2, 59.2, because that's my number of days, times lambda, which is my decay constant. So ln of 1/16 is going to equal negative 59.2 lambda. Lambda would then equal, and I know I've drawn lambda differently every time I've written it down, so lambda would then equal 0.04683 day to the neg 1. So that gives us the value of lambda, which I can then substitute into this second equation here. So so the half-life is equal to ln 2 div 0.04683, which also gives us 14.8 days. I personally find it far simpler to just work out 2 to the power of whatever it is. I personally think that's a much easier way to do this. However, it can be done the other way around in case you completely blank. You can work from this original equation. Okay. So there's two main types of nuclear waste. We have low-level waste and high-level waste. So low-level waste is things like the paper gown that you wear when you're getting an X-ray. So it can be like nurses' equipment, nurses' clothing, shoes, papers that have been in like radiologist's office. So low-level waste tends to be only mildly, it tends to have low radioactivity. It tends to be a less dangerous form of radioactivity, and also it tends to have a short half-life. In terms of disposal of low-level waste, basically you put it in a steel barrel and then you bury it in concrete. High-level waste is a different story. So high-level waste is what we get from like nuclear plants. Or as a result of meltdowns, or as a result of like nuclear weapons. So high-level waste is generally what we'd consider more dangerous. As you can tell about the names low versus high, it tends to be more radioactive in terms of the danger of the radiation it's releasing. It tends to have a longer half-life. And in terms of disposal, we do something called vitrification. So turn it to glass. That's what vitrification literally means. So we tend to vitrify it, and then depending on the exact location, they can be sunk to the bottom of the ocean in special containers. It can be in lead and concrete lined bunkers. It tends to be a more serious and longer term prospect though, because some of this high level waste will remain radioactive for the next 20,000 years or more. Whereas the low level stuff, you stick it in concrete for a few weeks and it's fine. The high level waste, we're talking about tens of thousands of years in some cases. So vitrification, lead, concrete. There is a history podcast I love called The Dollop, and in one of their episodes they talked about the nuclear plant, one of the nuclear plants in the US, and some of the ways they managed their nuclear waste were truly horrendous. If you're interested, let me know and I'll try and find the name of that episode. Let's continue on. So leakage of radioactive material can happen during transport, or if there's an issue at the power plant. So it happened at Fukushima, which is obviously in Japan, and it also happened at Chernobyl. So Fukushima happened relatively recently. Chernobyl happened when I was a baby, so quite a long time ago now. And it can also happen it can happen in a way that is in some ways unpreventable, and it can also be transferred out by workers. It can get it if it gets into water supplies, that's going to be an issue. It could be released as a gas unintentionally. One of the isotopes that can get out that's quite dangerous is 131 iodine. Now, iodine is important for the thyroid gland, and you can't see me, but I'm pointing at my throat right now. That's where the thyroid's located. And the thyroid takes up iodine as part of its function, and if that gets replaced with radioactive iodine, it's actually quite dangerous because it can cause like targeted cellular damage to the thyroid, and it can lead to thyroid cancer. Meltdown, again, that's Fukushima and Chernobyl. That's one of the issues we can have. Attack. So nuclear power plants can be a target for terrorist activities because they are the one place where you are guaranteed to be able to get your hands on uranium. You can also, just get escape of the radioactive isotopes, whether that's high level or low level radiation. You can also get contamination in general, so from storage. All right. Having said all of that, though, nuclear power does have its positive aspects to it. Once the nuclear power plant is built, it is largely a carbon neutral process. Additionally, nuclear power is stable enough. It isn't weather dependent in the way a lot of renewable energies are. And it is an option that would be able to support like base load power, and it does in many other parts of the world. Australia is not there. We have one nuclear generating station in Australia, and that's a research facility at a place called Lucas Heights, just outside of Sydney. Now, I would rather, everything I've talked about on this page considered, I would rather live next door to a nuclear power plant than a coal-fired power station every single day of the week. Because if something happens that's bad with a nuclear power station, it's catastrophic. Day to day, a nuclear power station is far safer to live next to. Last video, I talked about coal being a really dirty source of energy. That's in terms of particulates in the air, it's in terms of carbon dioxide released. Nuclear power really does have its advantages over fossil fuel-based methods of power generation. It's also, as I mentioned, more reliable in a lot of ways than renewables because there is a consistent power output. It doesn't vary depending on whether the sun's out or whether it's windy. So nuclear, and Australia also has certain benefits when it comes to looking at nuclear. Australia's got some of the largest uranium sources in the world. Unfortunately, most of those are under Kakadu National Park. Australia is also far more geologically stable than a lot of other parts of the world. So we would be able to store the nuclear waste in a way that's far safer. And also, because we are so geologically stable, we wouldn't have the same issues as was seen in Fukushima. We wouldn't have a power station that would be exposed to earthquakes. So yeah, nuclear safety is a concern, yes, but in general, it is a power source with some things to recommend it. So let's go through and highlight what we talked about. We talked about fusion reactions in the context of increasing binding energy. We talked about, we didn't actually talk about that. That might be something I bring up in our conference. And I talked about star composition. I talked about fission reaction and binding energy. I talked about fission reactions, critical mass, plutonium, radioactive waste, long and short half-lives, and half-lives. I constructed some nuclear equations, I explained in terms of binding energy, and I talked about atomic absorption spectra of hydrogen and helium. Okay, we deduced some nuclear equations, we explained fission reactions, we discussed storage and disposal of nuclear waste, and we solved a decay problem. Let's look at this guidance. So you're not expected to recall specific fission reactions. You don't need to know how a nuclear power plant works. The safety and risk issues I did talk about, so health, problems associated with nuclear waste and meltdown, and the possibility that nuclear fuels might be used in nuclear weapons. I then talked about these equations. Thank you so much. Have a fantastic rest of your day, and I will see you next time. Bye.